Welcome to Study Loop.
So here we have an adiabatic expansion for the argon gas, and we're going to treat this gas as an ideal gas. So it's just all axioms for the ideal gas, even though argon is actually a real gas, but it can be approximated as an ideal gas. So we have an adiabatic expansion. This means that the volume is increasing, so it goes from V1 to V2, where V1 is greater than V2. It's actually smaller than V2, sorry. V1 is smaller than V2 because it is expanding, but the pressure is going down. So the pressure 1 will be going to pressure 2. Well, the pressure 1 is greater than the pressure 2. So the pressure is decreasing and the volume is increasing. And we can plot this on the pressure volume diagram like this. So we have this initial point, initial volume, and initial pressure, P1, and we have the final volume and the final pressure, and here are their points. So this is the point 1, this is the point 2, and it goes from the point 1 to the point 2, point 1, point 2, in this direction. And this is the PV diagram for this process. So the pressure decreases, the volume increases. That this is the way that this process will go. Now we need to go for the part B of this problem. And here we need to evaluate the work done by this adiabatic expansion. So obviously the gas is expanding and it is doing the work on the outside of the system. So we'll start from the first law of thermodynamics. Q equals the internal energy plus the work done. Therefore, the work done is the internal energy subtracted from the Q, or from the heat flow. So since this is an adiabatic process, we know that the heat flow will be 0. Therefore, W equals minus delta U. And next, since we will use the equations for the ideal gas, and we will approximate that the change in volume is not very large, so we can use the heat capacity for the constant volume. This is an approximation to make these calculations easier. So we will say that delta U equals N times heat capacity for the constant volume and the change in the temperatures. Now we will convert the temperatures into kelvins, and we can substitute this to be N times CV T2 minus T1. So since we know all of these right-hand side parts of the equation, we can immediately solve for the delta U. And again, I repeat, this is an approximation, but a very good one. W will then equal this, just minus N CV T2 minus T1. Substituting the known values, we have that this is minus 0.45 moles, then times 12.47 joules per mole kelvins, times 283 kelvins minus 323 kelvins. And when we put this into a calculator, we can see that this is going to be minus, so the temperature is decreasing, and therefore the work done will be a positive value. This is 224.46 joules. So the work done is positive, and this confirms that the gas expands. When the gas expands, the gas is doing work on the surroundings, so the work is being done. And now for the part C of the problem, we will simply use the given what we already derived. So the internal energy is equal to the negative work done. And since for the part C of this problem we need to evaluate the internal energy change, therefore we can simply say this is equal to minus 200 of positive 224.46 joules, and therefore the delta U will be equal minus 224.46 joules. And this is expected because the change in internal energy is always proportional to the change in the temperature. Since the temperature is going down, the internal energy will be also, the change of internal energy will also be negative. And this is because the gas argon is isolated, and the energy consumed by the work done comes from the internal energy alone. There is no heat exchange with the surroundings, so delta U will also be negative for that reason as well. This is the end of the problem. We have solved it, and I hope you find this helpful, and I hope to see you in the next class.